In today's video, we're going to continue our discussion of structure and bonding with polarity and how that affects intermolecular forces. On the first day of class, we talked about several different types of bonds, and they included ionic, polar covalent, and non-polar covalent bonds. To determine what type of bond is formed, we're going to use electronegativities. And here we have the organic chemist's periodic table, which is very much abbreviated with the electronegativity values of each element listed below. And electronegativity, which I'm going to abbreviate EN, is an atom's ability to draw electron density towards itself in a chemical bond. So let's see how we can use this. I'm going to start with sodium chloride, which hopefully we all remember from general chemistry is an ionic bond. So if we look at our periodic table and the electronegativity values, chlorine has an electronegativity value of 3.0, and sodium has an electronegativity value of 0.9, and that leads to a difference of 2.1. For electronegativity differences greater than 2, we're going to call that an ionic bond. Let's think about a couple of polar covalent bonds. So one example I can think of is water, or H2O. Right. We're just going to consider two atoms, the ones involved in the bond. And so oxygen is the more electronegative of the two with an electronegativity value of 3.5. Hydrogen, on the other hand, has an electronegativity value of 2.1. And so that leads us to a difference of 1.4. And electronegativity values between 2 so electronegativity difference between 2 and about 0.5, we're going to call a polar covalent bond. Non-polar covalent bonds, a good example of that is a carbon-hydrogen bond, as in methane. Right, for carbon, the electronegativity value is 2.5, but for hydrogen, the electronegativity value is 2.1. That leads us to a difference of 0.4. And anything less than, where the electronegativity difference is less than 0.5, we're going to call that a nonpolar bond. Well, in these three examples, we've been really concerned with the numerical values of the electronegativity. Really, relative numbers are all that we're concerned about. And so when we look at the periodic table, remember that electronegativity increases as you go from left to right across the periodic table, and as you go from bottom to top on the periodic table. And the only other thing you really ought to remember is that hydrogen's electronegativity value is a little bit high for where it stands on the periodic table, and you should just remember that it is really closer to being above carbon on the periodic table. so that that CH bond that we're going to see so often in organic chemistry is considered nonpolar. Let's look at a couple of other examples. We'll start with HF, and that Lewis structure looks a bit like this, or just like this. And we can look at the periodic table and know, hopefully, that fluorine is the most electronegative atom, and hydrogen is one of the least electronegative atoms that we're going to talk about. And that means that the electrons in this bond are being pulled in the direction of fluorine. So one way that we illustrate that is using this weird funky arrow that's going to point in the direction that the electron density is being pulled. And we're going to put this little hash mark right above the positive side. So another way we might draw that is to give a partial charge. And so I'm putting a partial positive on fluorine, but that is incorrect. Fluorine is electronegative, and so it's pulling electrons towards it, so it is a negative charge. And the hydrogen in this bond is going to get a partial positive charge on it. And so that bond is polar, and it's polarized towards fluorine, making it a little more negative. If we look at SiH4, or that Lewis structure, looks something like this. And silicon is right below carbon, and we know that the carbon-hydrogen bond is nonpolar, and so we're going to assume that the silicon-hydrogen bond is also nonpolar. If we want to look at the electronegativity values, we could do that, and we have hydrogen that's 2.1 minus silicon that's 1.8, and so that is a 0.3. So that bond is nonpolar, and I'm not going to write anything to indicate a dipole moment with positive and negatives because it doesn't exist for silicon hydrogen bond. The last one I thought we would talk about before we start thinking about molecular polarity is CH2 Cl2. And this one. And here, we're only going to consider two atoms at a time. So we can first think about the CH bond, which we've seen several times, and we've seen that that's nonpolar. And so we don't have to consider anything about that. But we've got a carbon-chlorine bond, and that is a polar bond. Chlorine is more electronegative. If I didn't know that, I'm looking over at the periodic table and seeing that it's closer to fluorine, and so it's going to be more electronegative than carbon. And so it's going to be polarized towards chlorine, and both the carbon-chlorine bonds are going to be polarized in that direction. And so carbon-chlorine bond is a polar bond. If we want to think about molecular polarity, or what the molecular dipole moment might be like, we have to consider two different things. So molecular polarity depends on both the polarity of the bonds in the molecule and the molecular shape. So let's look at dichloromethane again, or CH2Cl2. Remember that carbon often, and in the case of dichloromethane, it is a tetrahedral center. And so I've got these wedges and dashes to indicate shape. If I want to think about the molecular polarity, I'm first going to consider the polarity of the bonds involved. And remember that CH bonds we just said were nonpolar, but these Cl bonds, CCl bonds, are polar. And they're polarized towards the chlorine as shown using those arrows. So that's the polarity of the individual bonds. If I want to think about the polarity of the whole molecule, I'm going to treat those two dipole moments of the two bonds like vectors. I'm going to add them together. And the adding of those things together is going to give me a big dipole moment that's pulling sort of just in between the chlorines, but towards the chlorines in itself. And so this molecule is definitely a polar molecule. But if we were to think about something like CCl4, that is definitely composed of polar bonds, right? We know that these chlorine carbon bonds are all polarized towards the chlorine involved. But the sum of those arrows, they sort of cancel each other out. They're all playing tug of war with one another, and none of them's winning. And so carbon tetrachloride is a nonpolar molecule, even though it's composed of polar bonds. Whereas dichloromethane is a polar molecule. So in order for a molecule to be polar, it must both be composed of polar bonds and be asymmetric. Right. So in the case of carbon tetrachloride, this molecule is completely symmetric. The Cl bonds or the carbon Cl bonds are evenly dispersed throughout the molecule, and so it's completely symmetric and non-polar. There are a couple of other molecules for you to take a stab at to see if they're polar on your worksheet. So go ahead and do that, and we will look at those together the next time we meet for class. The last topic of today's video is intermolecular forces and the factors that affect them. And so hopefully this is a review, but just in case it's not, let's look at the types of intermolecular forces that are possible. So the strongest type is ion dipole interactions. And for this to be present, you have to have both ions and a dipole moment present. An example of this might be a situation where you've got a sodium ion, which is positively charged, interacting with acetone. Acetone is has a carbon oxygen double bond, and that carbon is connected to two other carbons that are both CH3s. Remember that oxygen is more electronegative than carbon, and so this thing is going to be polarized in this direction, and there's going to be a partial negative sign or charge on that oxygen. And so that partial negative charge is attracted to the positive sodium, and so this is an ion dipole interaction and is a very strong interaction. The next strongest type of intermolecular force that we'll talk about is the hydrogen bond. And for hydrogen bonds to be present, there must be a hydrogen atom covalently bound to an electronegative atom. Those electronegative atoms that qualify are fluorine, oxygen, and nitrogen. So an example of this, we could look at ammonia. Ammonia is NH3. And that has an intermolecular force with another ammonia. Where the positive charge on hydrogen is going to be attracted to the negative charge to another nitrogen, like this. In this molecule, or the way this is drawn, I might call this hydrogen or this ammonia a hydrogen bond donor, and this molecule a hydrogen bond acceptor. In order for something to be a hydrogen bond acceptor, it just has to have an electronegative atom. It doesn't have to be have that hydrogen covalently bound to it. So acetone, which we saw in the previous example, can be a hydrogen bond acceptor. If it's in the presence of something like ammonia, where there's a hydrogen bond between the partial positive of that hydrogen and the partial negative of that acetone's oxygen. So this is a special type of the third intermolecular force, which is the dipole-dipole interaction. In order for this to be present, there has to be a polar molecule. So something like dichloromethane, which we've seen already, is polar. You've got CH2, Cl2, and those are going to interact something like this. Where the partial negative side of one molecule is going to be interacting with the partial positive side of the other molecule. So that's a dipole-dipole interaction. And the last type is London dispersion, or just dispersion forces. And these are the weakest type of intermolecular force. They involve typically nonpolar molecules, although all molecules have dispersion forces. We only think about them being a super strong or important force in nonpolar molecules. And that's going to be something like pentane interacting with another pentane molecule. They may stack on each other like this. And there is a very weak interaction between these two molecules here that holds them together. I want to talk for a couple of minutes about the things that affect the strength of intermolecular forces. And so the first one we're going to talk about is molecular weight. And to think about this, I want to look at, we just saw pentane. And how it interacts with a molecule, another pentane molecule. And let's think about, let's say decane, or carbon containing molecule that has 10 carbons. So that's 5, 6, 7, 8, 9, 10. And maybe they stack a little bit like so. The boiling point of pentane is about 35 degrees Celsius. The boiling point of decane is about 175 degrees Celsius. And so, 140 degrees difference. And the reason for such difference is the intermolecular forces in decane are much stronger. And they are much stronger because they have a higher surface area. And so one thing I want you to think about, dispersion forces are like Velcro. If you have a very small piece of Velcro, you could use that to hang a picture on the wall. But you couldn't say put a 10-pound weight on the wall with that same piece of Velcro. On the other hand, if you think about, there's this carnival game where you can put on a Velcro suit and run at this inflatable wall and jump and you stick to it. That Velcro suit has, much larger surface area than the 1-inch piece of square Velcro that you were using to hang the picture that won't hang up a 10-pound weight. But if you increase the surface area to several square feet of your body, that's much stronger and can hold up the weight of a person. The other big factor that affects boiling point for organic chemists is branching. What do I mean by branching? If we think about back to pentane, pentane has no branching. It's just a linear molecule, and it stacks on top of itself real well. Remember, its boiling point was about 35 degrees Celsius. Neopentane is an isomer of N-pentane, and it looks like this. There's still 5 carbons, 1, 2, 3, 4, and then the central one is 5. But the boiling point on this guy is about 9 degrees Celsius, so substantially lower. That's because we've decreased the surface area that this molecule can have. When we think about how it might stack with itself, right? In this particular case, if I draw another molecule right next to it, right, I've only got this little bit of contact between the two. And so there's not much surface area. There's not much to stick to. Whereas in neopentane, it's linear and you can get lots of contact. And so they are close together and have a much stronger intermolecular forces than neopentane does. So how do intermolecular forces affect physical properties? We've already seen this a little bit with boiling point. As intermolecular forces increase, as IMFs increase, the boiling point is also going to increase. We see this trend with melting point as well. As intermolecular forces increase, the melting point increases. Viscosity, which is the ability of a liquid to resist flow, as intermolecular forces increase, viscosity also increases. And the last thing we want to think about is vapor pressure, which is the pressure of a gas above the liquid. And as intermolecular forces increase, this time vapor pressure decreases. That's going to wrap up today's video. There are a few more practice problems for you to look at. Take a stab at those before next class, and we will go over some of them together.